here first, we're back in the car and spend it.
How to like basically contact.
Yeah, this is basically the same as what the car is doing, and picture the screen. Yeah, pretty good.
So that's the thing. I love the application. It's very motivating. Assistive. I really like that. Like
yesterday we submitted to Argall, and I finished submitting on 1:30, right? So I'm like totally dead, and I go there and go home. So I just walk home like that and stuff, and I see now the robot. So there was a scene on the right, walking home, back to the end. I didn't see it, I heard her, I saw a car like speeding away, and I heard her screaming. And so then I had to
watching at that time, definitely can't be whatever.
yeah.
But then yeah, you should take over and live, no? So much money.
There is escort.
So anyway, so I had to stay late because first of all, count her down, and then I had to call 911 and stay staying. So now today I'm like, I mean, you know. Oh, how's it going with you?
Searching for advisors. Probably co-advising Maxim and Maxim grade. How is it going when you just submitted? What did you submit? High level? What did you submit? High level?
Weight expression motion. So you know, uncustomizable motion?
Yeah, motion. Goal. How to know?
Some similar idea when you have objects in different ways, how you can move the text in a way that's a kind of that the observer can do it and maybe drop it.
Oh, like how to list like heavy object.
But then I'm like, yeah.
What is the application? Because a human could the gauge, if it's another human, I can understand that the human might offer to help if it is a very heavy object, but the robots.
So, like for example, like if it's a heavy object, the robot finds it's a heavy object, and if you can tell whether the object is heavy or not, you can prepare it. It won't save the world, but it's fine. It's fine.
I thought the other way, but yeah, it's for
And it's good to have a paper on it, right? Last project. It's the best thing that I could.
There's one here and there's two.
Although I have to say, it's a lot of more. I think they won't sit for me. I think it proved a lot more work than I initially said. So I thought that like I thought it's like it's just like problem, I'm just and then like I sent for review and they were like now do this, do that, change that, and I'm like so try not to push for the next
But maybe we have like a stay healthy. You want to be able to face your PhD.
I don't want to become burned
But next year is the gonna be in the gym.
Vienna.
Vienna. That's so super interesting. Okay, go there.
It's not New Zealand, but I don't know, I've been to Glasgow several times, so it's not very Yeah, sure, yeah. Do you want me to sit there or? Oh, yeah, sure, absolutely. Yeah, absolutely.
So we are going to start, and it's my great pleasure to introduce Brenna Argall. She is the Jane and Donald Brewer Professor in Electrical Engineering and Computer Science at Northwestern University. And Brenna also happened to have been co-advisor in her PhD by me and Brett Browning. And she was also an undergrad at CMU, she has a degree in math, I believe, math, right?
Yep.
And then she did a master's in robotics, and then a PhD in robotics. And she is a tremendous researcher in terms of she did robotics, then she went to EPFL for a postdoc after she finished her PhD, doing a lot of effective computing and robotics in human robot interaction. And now she's the most expert in rehabilitation robotics in the world. So let's welcome Brenna.
Thank you. Thank you very much, Manuela, for the very kind invitation, and all of you for coming to the talk and for inviting me. It's a real honor to be back at my alma mater giving the RI seminar. So Manuela just mentioned that I'm also at the Rehabilitation Institute of Chicago, and my appointments at Northwestern actually also split between mechanical and PM&R, which is a department in the medical school. So the Rehabilitation Institute of Chicago is a rehabilitation hospital. It's been the #1 ranked rehab hospital by World News Report for 26 years. And what this means for me as a researcher, or for any of us engineers as researchers there, is that we have very ready access to expert clinical advice. So we can just ask an occupational therapist if they have time later this week to just pop up for 5 minutes and give us their opinion on something that we've been developing, which creates much faster turnaround cycles, which is very lucky. And then we also have access to a much larger patient pool of people to evaluate our devices. So in general, many of the type of impairments that we treat at RIC are fairly rare to see in the population, but we attract patients from around the world, actually. So we have a higher concentration of these impairments than you would just see in the Chicagoland area, which is also an advantage as a researcher. So when I arrived to RIC 5 years ago, I was coming from the field of robotics autonomy. So I was trained here and at EPFL. I was doing robot learning from demonstration, very much in the field of autonomous robotics. Within the field of rehabilitation, autonomy is not represented very much, at least not clinically. So clinically, the kinds of robots you see tend to be therapy machines, or they tend to be like prosthetics and orthotics. So they're always human controlled, or they're very repetitive. There's no sort of higher level autonomy. But what we do see is that there are machines that are meant to be human controlled that are difficult for the humans to control. So here's an example of many assistive machines that we see in rehabilitation that are meant to be controlled by the human. So by far the most ubiquitous is the powered wheelchair. This is a two-dimensional control problem. You control speed and heading, and so it's very naturally covered by a two-dimensional joystick, or a two-axis joystick. And people who can have the full hand function to operate a two-axis joystick, the wheelchair very naturally becomes an extension of their own body's mobility. Now, if you don't have that kind of hand function, you are forced to use alternative interfaces that are more limited. So one common one is the sip and puff. If anyone has ever seen someone try to drive a wheelchair using a straw-based interface, so Stephen Hawking used to use this kind of interface, what that amounts to is basically operating one dimension at a time, and it's a discrete interface, and it's what's called non-proportional. So if you blow harder, you don't go faster. So now you're operating like speed and heading individually, usually. There's tricks to get around it. And if you want to actually change how fast you're going, you have to puff your way back through a menu. There's normally a little screen mounted on the armrest. You have to puff your way back to a menu and choose a different power level. And there's typically like 4 power levels. And so this is very taxing, and it can make wheelchair operation much more of a burden for the user, especially if you're in scenarios where you need to do like dexterous maneuvering. Now that kind of problem gets confounded even further if we are now talking about a more complex assistive machine like a robotic arm. So this is the Jaco in this picture, Jaco robotic arm from Canova Robotics. Many of you have seen this robot now. This was intentionally developed for rehabilitation purposes. It's meant to be mounted to a powered wheelchair. It happens to also be a nice robot for robotics research, but that's not why it was originally designed. It is sold with a 3-axis joystick, which that means the joystick also has twist. But this, of course, only covers half of the control space if you're trying to position and orient the end effector, right? That's a 6D control problem. So you end up doing what's called control partitioning into different control modes. And so maybe you control just position, and then you have to push a button, and you control just orientation, and you push a button again, and you have to toggle between these control modes. And that's when you can operate 3 dimensions at once. Of course, many of the people who would benefit from an arm like this don't have that kind of hand function to operate a joystick with twisting and being able to move like this. If we now consider those more limited control interfaces that I was talking about that are used to drive powered wheelchairs, those just are not used to operate these kind of arms. It's too taxing to try to operate 6 dimensions individually. And so what we now see as a result of this is a paradox where the machines that likely would benefit a certain patient population the most are inaccessible to that patient population precisely because of their motor impairment. And this is an opportunity for robotics autonomy. So if we can turn these assistive machines into autonomous robots that share control with the human user. So the human user is always still in the loop. We know that the humans want to be in the loop. They don't want a full autonomy solution. But if we make these systems that can control themselves, and share control with the human, then we can hopefully offload some of the control burden from them, perhaps even make these assistive machines accessible to people whom they are not currently accessible to. So how do we turn an assistive machine into a robot? Oh, sorry. So just to recap, these control challenges that I mentioned on the previous slide. So first, we have these limited interfaces that I mentioned. So right here is the sip and puff that I talked about. There's also head array-based interfaces, which are basically switches that are in the headrest. And so you tap back to go forward, you tap right and left to go left and right. If you need to go backwards, you maybe do a double tap back. You can sort of cheat if it's positioned properly and maybe activate the back and side panel at the same time, and then you could get a 2D control signal, but not necessarily always. Then we have the motor impairments of the user. So regardless of the interface that they're using, the motor impairments of the user are probably masking their true motor intent, perhaps filtering it as well. We have machine complexity. So we've got this paradox I mentioned earlier where likely the more motor impaired a person is, the more complex the assistance they require is, which means that the machine that will provide that assistance is more complex, which means it's more complex to control. And yet, it's harder for you to issue control signals of higher complexity because of your motor impairment. So what we'd really like to do is leverage all these advances that we've made in robot autonomy as we've gone from robots in the factory to robots being in people's homes and future domains where we really want robots working side by side with humans. In order to do this, we've had to come up with synthetic ways to accomplish sensing, cognition, and also actuation. And what we would like to do is leverage these synthetic approaches to address impairments in the sensory, cognitive, and motor systems of humans. All right, so how do we turn an assistive machine into a robot? It's going to be no big surprise to people in this room. We first need to add sensing in order to sense the external world. We have to add on computing and AI in order to reason about that sensory information and also the control signals that are coming from the human. And then we've turned our assistive machine into an assistive robot. Now, all of these control challenges that I mentioned before that are challenges when the human is just trying to teleoperate the machine are also challenges for our autonomy to try to interface with the system. We also have one additional challenge as well, which is that our humans have non-static abilities. So we know that our humans are going to be changing over time, either because they are in successful rehabilitation and they're gaining function, which is of course what we hope. They might have a degenerative disease and they might be losing function, which is what we don't hope for, but it's the reality of the domain we work in. They also are probably likely changing in the amount of assistance that they'd like day to day or even throughout a day based on things like fatigue or pain. And then also every human just changes over time in how they interact with automated systems in general. And so what we want to do is be actually responsive to that. I think actually that's going to be a linchpin in this kind of technology being adopted out in larger society, is being responsive to the fact that the amount of assistance that people want is going to be changing over time. So these are the robot platforms that we're working in my lab. We started out with this wheelchair platform that's actually just built on the base of a powered wheelchair. So this is a development platform. You'll notice that it doesn't have a seat. That came along last summer when we got a second platform, and my postdoc ported our sensory and software system onto it. It is, and this is what we can now use to do subject studies with motor impaired patients who can't, for example, walk behind the robot while they're teleoperating it. Here we have the MECO robotic arm, which I mentioned earlier, which was developed specifically for assistive applications. And then this arm, which I'm not really going to talk about any further in the talk, but this is a neat arm that we've just only recently got. It's through a collaboration with Antonio Bicchi at the University of Pisa. So if anyone's ever seen the Pisa IAT hand, it's that hand on a sort of compliant arm base. And so what's really neat about this hand is that you get all this extra hand functionality for just a one-dimensional control signal, because it has the first muscle synergy, motor synergy of the human hand. So this is the first motor synergy of the human hand. It has that encoded and operated by one motor. And so basically, with the same complexity of operating this two-fingered gripper, we get way more hand function. So that's going to be really interesting to look at how that plays out in our lab, but we're still figuring out how to control it. So, oops. All right, so I'm going to chat really briefly about the wheelchair platform we've been working on. So we have been prioritizing customization and low cost in the robotic wheelchair that we've been developing. So customization, I've already talked about why that's important. So each person is different in their individual abilities, in their preferences, and also actually in their bottom line financially. And we also expect that these are changing over time. Low cost is necessary because we're not expecting that this is going to be covered by insurance every time or anytime soon. So when a patient gets fit for a powered wheelchair, a therapist will fill out a stack of forms this thick that justifies every cushion decision, every aspect of the control interface, everything, and that's the only way it'll get reimbursed by insurance. So the only way we're going to be a part of being reimbursed by insurance is if we make it into that packet. And that actually is my end goal, is that I will consider that we've sort of made it with robotic wheelchair research when autonomy is a part of the options that you have on insurance reimbursement forms. But in order to do that, we're going to have a lot of studies that look at cost-benefit analysis and whether this amount of autonomy means that you are less dependent on caregivers by this amount and has this amount of cost savings, and that's going to take a lot of time. So we are prioritizing using commercial products, and this needs to be financeable out of pocket by at least a good portion of the population. So something like a laptop computer is reasonable to think of. So in terms of customization, we're accomplishing customization using a modular software suite where we have different assistance modules that people can opt into or out of based on their needs or preferences. We also have ways to share control between the human and the robot, and those ways to share control are parameterized. And so these parameters provide tunable knobs that we can customize to each person. And in our future work, we're starting to look at adapting all of this over time, and I'll talk a little bit more about that at the end. One of the ways that we're making cost lower is by making sensor modules customizable as well. So the idea is that we need at least one sensor, and normally for us that is an RGBD sensor like an Asus Extion. And so that's our base system. If you add on additional sensors, you might unlock additional capabilities that were on the previous slide. You also will probably add robustness, but of course that comes at additional cost. And then we have sort of a base amount of computing power and electronics. And we've recently won an NIH SBIR that's a collaboration with a company. So hopefully we'll actually start seeing some of this technology come out of the lab soon. Some of our work is about just enabling autonomy with goal perception. I wouldn't say this is a core research focus in my lab, but it's sort of just a necessary thing to get working. And we've done this for the wheelchair and as well for manipulation. But really the big research questions in my lab are the following. So first is how to appropriately share control with the human. So I mentioned that this really needs to be customizable. We know we can't take away control from the human when they want to be in control. Then we're actually making them less able, which is entirely not the point. We can't give them control when they're not expecting it because it's dangerous. Exactly how to get this right is a huge open question, and there's a lot of research that needs to be done in this area. And then the second is how to adapt this over time. So the control sharing, or maybe just the control itself, the autonomy itself. How do we adapt this over time? How do we adapt this to different people? So I'm first going to talk about control sharing. Most of my talk's actually going to be about control sharing because that's where most of our work has happened so far. So one of the really basic ways that we do control sharing is just for safety. So if you watch my thumb here, you'll see that I'm always trying to drive the wheelchair forward into the chair. And what's happening is that we are just sort of forward projecting my command and creating a sort of temporary sub-goal. So we aren't trying to infer anything higher level than that about what the human's trying to do. This is just a very basic low-level functionality. What happens is if that goal ends up in an obstacle, we sort of iteratively shift control away from the human. So this alpha factor is dictating how much control lies with the human, which is green, full teleoperation is in green, and how much lies with the autonomy, where full autonomy is red. And so it's really just if a collision is really imminent that we take control away fully. Otherwise, we do it iteratively, just to try to not wrench control from the human. One thing that we're in the middle of doing right now is a comparative study between different ways to share control. And this is something that we really don't see much of in the literature, but we think is probably pretty important to start investigating. So oftentimes what we see in the literature is a comparison between full autonomy and shared control or full teleoperation, no autonomy and shared control, which are also important comparisons to make. But the thing is that this question of whether or not the way we shared control is like the right way to do it or the preferred way to do it, we often don't see a lot of comparison of that. So that's something that we're in the middle of doing right now. So far we've run 5 spinal cord injured subjects with high spinal cord injury and 5 uninjured subjects. It's just a doorway traversal task, so it's always the same task. And what we're doing is we're comparing 4 different ways to share control to teleoperation, and also using 2 different interfaces. So on the right here, we're using that head array interface that I mentioned, that sort of switches embedded in the headrest. And on the left, we're using a joystick, where in this case, the joystick also was modified with a T-bar, just so that this patient could operate it. And this is full teleoperation. So this is what the patient's using for full teleoperation. And I should mention that this patient actually used a head array for 20 years and then has now been using a joystick for 5 years. Now granted, this is not his chair, it's our chair, so he's not used to it. But you can see how difficult it is to maneuver through the doorway when your control signal is masked by your motor impairment, and using these limited interfaces, it's even harder. So one of the questions we're interested in looking at is whether or not this question of control sharing varies based on the control interface that you're using as well. The difficulty of that interface and also the kind of signals you get from that interface. Where on the right, this is a discrete 1D signal, and on the left, this is a continuous valued 2D signal. And then we're looking at these 4 different ways to share control. So, and we took these sort of from the literature, ways which we've seen control sharing implemented often within the literature. So the first is just filtering. So we're just doing that forward projection of the goal that I mentioned before, and we are just capping the user speeds to never exceed the autonomy speeds. The next one is a blending with this immediate goal. So here it's at the autonomy is generating a safe path, and the user is doing its own path, and we're blending it. And this is really kind of what I showed you in that earlier video about safety. It was kind of this blended approach with just an immediate goal. Then we're doing that same blending approach, but now we're using a perception goal. So we have a perception algorithm that's able to identify the position and orientation of the doorway, and we're using this as a goal now to this high-level planner. And then we also have a sort of more autonomy-intense version of that high-level perception goal, where we're doing the blending, but then also once we get close enough to the door, if we're really confident that that's what you want to do, and you stop giving us a control signal, we'll just take you through without you giving any control signal at all. And oops, there we go. And this is what the approaches look like. So I'm not going to present any data yet because the study's ongoing. What I can say is when you look through this, you might be able to see some differences in performance. But it's not that one necessarily looks more successful than the other. And so if we were trying to choose between these as engineers, it would seem like somewhat of an arbitrary decision if we were just doing it based on the performance of the system. What we are seeing, however, is that people definitely have preferences. So we are asking them to tell us which one they like the most, and ties are allowed. So if they wanted to say they liked them all equally, that would be allowed, and which one they like the least. And we are not seeing a definitive preference for one over the other. There's sort of like some tend to be more favored than others, but there's none that's never chosen, and there's none that's always chosen, which is starting to tell us that actually we're probably going to need to involve the user in this process, that this is something that's individual to different users and might be a product of things that we can't compute through sensors.
Quick question.
Yeah.
How much practice, or was there any training? for these different controllers? It seems like it might take a little bit of time to figure them out.
Yeah, so we did do, so this is a 2-day or like a 2-session subject study. So we are looking at whether or not there are effects from learning session to session. And they practice a little bit with driving around with each interface before. And then we gather two runs where each run consists of going through 4 doors with a given system. So we can also look at it sort of like within, like if by the time they go through the 8th door, if they're doing something performance difference compared to going through the first door. So far we're not, we're seeing some learning effects. We can't say anything like confidently in terms of statistical significance because we're still running this study. But yeah, certainly like familiarization with autonomy is going to be a big factor as well, which was one of the reasons why it probably also needs to be changing as users get more familiar with it. Okay, another study that we did was with the Miko robotic arm. This was an exploratory study that involved spinal cord injured subjects and uninjured subjects. And what we were looking at was ways to customize this arbitration function. So this form of an arbitration function is something we see a lot in the literature, where if alpha is dictating how much control lies with the human versus the machine, what alpha is dependent on is how confident the machine is that it can predict what it is the robot or the human is trying to do. And so it's a function of being able to predict human intent. And so we don't necessarily think that control sharing is this simple, that it should only be based on whether or not the robot has figured out what you want to do. It's probably based on more complex concepts like task difficulty and stuff like that, but we'll get to that. And so now this is a function that is parameterized by 3 parameters. So one is at what point does assistance kick in? What point does the robot start helping? The slope of this function defines how quickly the robot ramps up the help it's providing. And then how high that bar ends in the end is telling us that once we're really confident, does any control lie with the human at all? Or how much control lies with the human? So you can imagine we get different functions with different parameterizations. What we did in this study, it was an exploratory study, and we let people verbally modulate these functions. So they were just telling us, I wanted the robot to take control earlier, I wanted to take control faster, and we would tweak these parameters just to kind of see what sort of functions they were coming at. There was a sort of minimum assistance level and a maximum assistance level that we tested as well as sort of a comparison, and then this customized function lied somewhere in between. And we did 2 rounds of customization for 2 different tasks. So on the top here, we see what this looks like with teleoperation. So he's teleoperating, I believe, in the 3-axis control mode. What you see right now is that he is performing a mode switch. He doesn't have the hand function or the finger function to be able to push on the button to perform the mode switch. So he is wearing what's called a utility cuff, and there's a pen inside of it, and he's using that to perform the mode switch. So you'll see he does the mode switch, and then as he starts teleoperating again, it ends up that actually he's not in the mode that he thought he was. So he has to perform a second mode switch. And this often happens, that it's hard to remember sort of which mode you're in. The Canova joystick actually provides some visual feedback on this, which we did not have in this study. So that's what it looks like under full teleoperation. You can see that there's multiple mode switches that need to happen. Here we have him using an arbitration function that he customized himself. So now that the autonomy is helping, one thing you notice is that you don't need to have any mode switches. Now this is partly lucky. It partly depends on the mode that you started out in and whether or not that mode was one in which you could disambiguate the goals, right? So if I'd started out in a rotation mode, I maybe wouldn't get any information about which goal I was going towards. But he happened to start out in a mode that was informative for disambiguating these goals. So just a couple of results quickly to share about this that I thought were the most interesting outcomes of this study. So one was that the difference between the spinal cord injured and uninjured subjects was diminished with assistance. So as assistance got more aggressive, so here's teleoperation, here's sort of an arbitration function that helps out the sort of minimum amount. Here's an arbitration function that helps out the sort of the most aggressive amount. We see that the statistical significance between these 2 subject populations is going down. So black is uninjured subjects and red is injured subjects, and this is task completion time. But what we see is that there's actually no statistically significant difference between these subjects any longer when they are now using the customized function that they figured out on their own, which was surprising to us. If you had asked me which was going to eliminate the function or eliminate the difference the most, I would have said max, because max is where the autonomy is playing the largest role, and the autonomy is same for both subject populations. And so I would have guessed max. And this is interesting. I can't really say much beyond that, except for that we need to look into it further. Second is that there was actually a difference between the two subject populations in how they performed the customization. So I had mentioned that there were 2 rounds of customization, and we can kind of look at the parameterization of this function and see whether or not they were customizing for more or less assistance in comparison to their first round of customization. And what we saw was that uninjured subjects actually customized for less assistance, while injured subjects customized for more. This was also somewhat of a surprise for us, because while on the one hand it makes sense because you think people have more, if they have more injury, or if they are injured in the first place, it's harder for them to operate the interface, and so they would want more help. But there's also a lot of data and studies that we've seen where people actually also want to remain as much in control as they can. And so I think that this is a good example of how this is sort of a balancing act, that we need to balance these 2 things, and it's sort of different for each person. And we did see an associated performance difference where the uninjured subjects, because they wanted less help from the assistants, their performance actually got worse, whereas the performance of the injured subjects got better because they had more assistance, which was also just interesting on the sidelines. We also saw that there was something that was interesting. So I mentioned that there were these 2 rounds of customization for each subject. So total we had 34 rounds of customization. What was interesting is that 7 of these 34 customization rounds had greater task completion time than max, which is the sort of most assistance you can be having, and that 14 of 34 customizations have more mode switches than max. And so what this is telling us, I'd say task completion time and mode switches are both sort of parallels for time minimization and effort minimization, which are things that we are commonly minimizing for during the optimization that we do in robotics, right? When we have to build a functional that's being optimized, we're often optimizing these 2 things. So this is kind of suggesting that perhaps humans are optimizing for something other than what we would normally be optimizing for as robot designers. I can't tell you what that is, but I think it's an interesting thing to know and to start paying attention to. And so our next steps are that we're trying to formalize this optimization procedure a little bit more. I had mentioned it was just verbal. Now we've got these different sorts of interfaces like knob and slider and button interfaces, and we're going to allow people to customize in sort of different ways, customize different functions, allow them to do it at any point in the procedure, and we'll hopefully start to see some patterns emerge for how often people want to be performing customization, at what level they want to have their hand in the game in performing this customization. Okay, so another thing that my lab has started looking at quite a bit is the trust in the human. So oftentimes we hear about this in the reverse, in systems that are shared control or that are just interacting, where humans and robots are interacting together. We hear about whether or not the human trusts the automated system. One of the arguments that we're making in this work is that actually the reverse is extremely important as well. That when you have human-robot teams that are operating with limited control or limited communication channels, that the understanding of each teammate, of the quality of information coming from the other teammate, is really essential. And we're looking at this in 2 different studies. So one is a collaboration I've had with Todd Murphy at Northwestern for a couple of years now. And we started out by asking the question of how much should a human be allowed to allowed to interact with a controlled machine. So you could imagine here, these are just mock-ups, but if we had a robot that was able to stabilize to a certain trajectory, now the human demonstrates something else, and it's not something that the robot can stabilize to. Perhaps it should only just take an iterative step in the direction of that trajectory, for example, unless it really trusts the human to teach it something new. And then you would maybe take a larger iterative step. So we've been doing work where we have a computed measure of trust in the human, and we're using this to adapt the allocation of control between the human and the robot system. We're thinking about this in the context specifically of very highly dynamic systems. So a good example are fighter jets, that these actually can't be controlled just by humans. The dynamics of the system can't be operated by a human as full teleoperation. They need some autonomy stabilizing the system. Oftentimes, when that's the case, if the human is able to disturb the dynamics at all, lots of times the dynamics are just dumbed down. So in like this crane example, it would be that you just move the payload very slowly instead of taking advantage of the fact that there are dynamics that you can, for example, swing it up into place or something. You can leverage the dynamics, but that's often not exploited. Similarly with exoskeletons. So this is now a shared control system where the human is perhaps providing an indication of what kind of gait cycle you should be in, but the stability of that gait cycle is managed by the automated system. So we did a study in simulation. I'm not going to get into this hardware platform. It exists in Todd's lab, but it's basically, there is a real hardware platform that this is mimicking you can think of it as being similar to a crane with a payload. We had 22 participants, and we had 2 trust paradigms, where for both of them, we started out by estimating the trust at the beginning that we should have in the human operator. And then in one group, we just kept this static for the entire time. And then in the second group, this became adaptive, where we were constantly adapting it after each trial based on the performance of the human. And 2 interesting things that came out of this study, which is that one, that adaptive trust lowers controller effort. So basically, when the trust was adaptive, the human generated trajectories that were easier for the controlled system to track, which we could interpret as the human having a better understanding of what the system was trying to do. What's also interesting is that this happened regardless of whether or not our initial estimate of the value of a trust was an overestimate or an underestimate. So for some people, the final value that they ended up in was higher trust than they started out at. In some cases, it was lower trust. But in all cases, adapting that trust, whether it was to higher or to lower, actually lowered the controller effort, which is an interesting thing to have come out of this. Okay, another project that we're just getting started under a new grant from the ONR is thinking about communication channels and whether or not we can trust the quality of communication channels. So we're used to thinking of, and this communication channels between humans and robots. We're used to thinking about communication channels in terms of distance, being challenged by distance. We're used to thinking about them happening in difficult or adversarial environments, that they are challenged there. One of the sort of arguments I'd say we're making in this project is that a lot of these challenges are similar to what we see when people with motor impairments are trying to operate assistive machines with limited interfaces. That these are perhaps noisy communication channels, that they are limited in some way and constrained in some way. And so what we're doing in this project is we are coming up with ways to compute sort of measures of trust in the quality of information coming from the human, including the quality of information along the communication channel. And we're going to use this to sort of decide whether or not control needs to be allocated more to the autonomy or more to the human. And also we're going to use it to temper learning. And so that's another thing I forgot to mention on the earlier slide, that I think that thinking about trust in the human is also really important within the context of humans teaching robots, whether or not that's a good teacher or a trustworthy teacher. And so this system's also going to be learning and adapting over time in response to signals that seem from the human, and that's all going to be tempered by this computed measure of trust. Okay, so far I've been talking about shared control largely. So now I'm going to shift to talking about how to adapt this control. So I'm going to take a step back and talk a little bit about my work before I came to RIC and Northwestern. So I mentioned that that's sort of when I entered the world of rehab. And before that, I was doing a postdoc at EPFL working with the iCub, and I was doing my PhD here working with the Segway. And in both cases, at a high level, what I was doing was figuring out ways to correct robots' motion after it had been demonstrated. So on the left, we had sort of a tactile interface that we were using to move the position of the robot. So this wasn't a back-drivable robot, so we couldn't correct it in that way. And so it was responsive to our touch, and that's how we provided position corrections. In my PhD, we had developed this sort of language, or this formulation that we called advice operators, where basically you could take a chunk of an execution and then also select an advice operator, which was actually a mathematical formula, and it would spit out a whole bunch of new demonstration points that have been modified, that were basically the executed points modified by this function, and use that to rebuild your policy. And we used these corrections in a bunch of different ways. So first, the first logical step was to use it for policy refinement. So if you had demonstrated something and then you wanted to improve the behavior of what you had demonstrated, you provide corrections in that case. We also used it for policy reuse, so to kind of bootstrap. If we wanted to start out with a policy that we already knew how to do, and we didn't want to start demonstration from scratch, but we wanted to just provide a correction, but have it take more immediate impact, or like have it have more immediate impact than it would if we were only just trying to do refinement. And then we also used it for policy scaffolding, where we would demonstrate motion primitives, but the system had no idea about how to sort of manage transitions between these primitives. And just on the fly, as it was executing, we provided corrections to help out with that. And so a lot of these ideas are now starting to come full circle back into the research in my lab in rehabilitation and assistive robotics. And that's because we're interested in this question of adapting control. We want to change the control over time. We want to do it in response to the humans. But but they're communicating with us over these lousy communication channels, right? These lousy interfaces. And so what this essentially amounts to is robot learning for motor impaired teachers. And this is something we're really excited to get working on. I don't really know of any other work in the field that's looking at this. And I think it's a really big question about what machine learning looks like when these are the teachers that you have providing data. So one big question is how to adapt. So with the iCub, we had this tactile interface where someone could sort of touch the interface, and that we use that in order to change our regression model. And that sort of interface for how the human communicates information to the robot certainly would not necessarily be appropriate in a domain where people struggle to move. And so what actually are the interfaces that we're going to be able to use, and what the feedback signal looks like when it's coming along those interfaces, those communication channels, I think is going to be a real big question to answer. And then also we expect that people are going to want to be able to define new robot behaviors. So especially for manipulation, I think it's very, very reasonable that people are going to have an idea of what they'd like the robot to do. So demonstration learning is a very natural way for people who are not experts to be able to provide demonstrations. The thing is that we normally think that even if people are not robotics experts, we normally sort of assume some level of task expertise. And that's something that we might not even be able to assume in this domain. So coming up with machine learning techniques that can handle that, perhaps even exploit that, is going to be a big focus of this project. And so again, if we have these limited interfaces and the motor impairments, what does demonstration look like in that kind of a domain? One final project that we're working on for adapting control is a collaboration with Sandro Musovaldi, who's also at Northwestern and RIC. Sandro's group has developed something that they call the body-machine interface, which is basically a vest of IMUs, and it's worn, and it kind of turns the body into a joystick. And so what it can do is detect very subtle movements in the shoulder. So it's actually able to be operated by people with very high spinal cord injury who are quadriplegics. And lots of times, if it's an incomplete injury, lots of times you still have a little bit of residual movement in your shoulders. It can pick up those very subtle movements. It's a vest of IMUs. They project it down to a lower dimensional, like a 2D space, and they've used this to control the position of a cursor on a screen. They've used it to do like typing on a virtual keyboard. They've used it to drive a powered wheelchair, all 2D control problems. What we would like to do is have it control a robotic arm, which is a 6D control problem. Now, we don't even know actually if this is even feasible. I know that I can certainly think of like 4 distinct axes that I would use to control with my shoulders, and I'm a person who has no motor impairments. What it would look like to introduce a 5th and 6th axis, and how intuitive that would be, I'm not sure. So we're not even sure if this is going to be possible, but the way that we're going to try to make it happen is by leveraging robot autonomy to help with the human motor learning. So what we would do is have the robot autonomy step in, fill in the rest of the control signal. When the human robot team is sufficiently able, then we step back a control dimension and pass that back off to the human. And we do this in an iterative way over time, and hopefully that makes it so that the human is able to take over more and more of the dimensions of control. What we like about this approach is that we're actually using robot machine learning in order to elicit human motor learning, which I think will be really neat to see if it works. We've demonstrated the integration of these two technologies. So here the body-machine interface was still just providing a 2D control signal. The control signal is being used to control the speed of the execution and also the transition between piecewise trajectories. So we defined piecewise trajectories for this task, and the person needed to decide when to transition between them. And then just as sort of a little pilot experiment, we modulated the position of the bowl so that people had to time the execution or like the transition at the right time in order to get it in. So you'll notice that his shoulder movements are really large. That's because he has no motor impairments. And so it's actually encouraging you to use the full space of your motor ability, which is another really nice thing about this body-machine interface, is that you have to move to use it. So in comparison with like a brain-computer interface, it actually is promoting motor rehabilitation by operating the assistive machine, which also we think has some potentially really interesting benefits. Sandro's group is actually already performing a clinical trial to see how much benefit you can have by using this machine, but he hasn't used it with robotic arms yet. Okay, so just to return to my earlier slide, I mentioned that we have these control challenges in this domain of physically assistive robots that are meant to, or physically assistive machines that are meant to be operated by humans, that we are addressing these first 3 limitations or challenges by introducing autonomy. And the big question when we introduce autonomy is how do we actually accomplish the control sharing? Then we also have this challenge of non-static abilities, and in this case we're going to be performing adaptation, but this question of where the learning signal is coming from and actually what they look like is also a big unknown that we're going to be researching in the coming years. So with that, I'd like to thank the current and former members of my research group. We're in Chicago, as I mentioned. We've got a great lab space right in downtown Chicago, so if you're ever there, feel free to come visit, and I believe that's it.
In fact, I forgot to mention this at the beginning. I visited Brenna. It's like, wow, we are in the penthouse of Chicago.
It was pretty lucky.
Like the whole 360-degree view of the lake.
Yeah.
On the what, 17th floor? Or
17th floor,
17th
yeah.
floor, there you go. So, and I also forgot to mention and congratulate Brenna for the NSF Career Award.
Thank you.
Which is just, so, any questions?
Yeah.
Does this make you think about the driverless cars and discussion happening today about the camp who wants no controls?
Yeah.
The other camp who wants to choose the control?
Yeah, so
I
certainly.
thought that the question was whether the autonomous cars would produce more of these disabled people.
Let's hope not.
I love more disasters now, you have more patients to work with.
So certainly it's the two domains are related in that way. I'd say in my domain, nobody even really considers seriously about cutting the human out. There might be scenarios where the human wants to be cut out. We have not seen them, but we also have not had systems that were fully capable enough to be out and about in people's personal lives where they had time to really trust it. And so these things might change over time. We don't really know. In terms of the level of which we've been able to assess things in the lab, full autonomy is not wanted or needed. And there's definitely with smart wheelchair research that happened like 15 years ago, they saw that it was really not well accepted. I think that there's an important thing to keep in mind in this domain is that the people who are interacting with our machines are not necessarily technology enthusiasts, right? Which is not the case with a lot of human-robot teams. Lots of times you have a human who's very willing to accommodate to deficiencies in the robot, but that's not why people are using our machines. They're using our machines because they have a motor impairment. And so that's one big difference. So in our case, we don't even really consider cutting the human out. And so that's why we immediately emphasize how do you perform shared control. It's true that sharing control is hard. It would probably be easier to cut the human out here. I think it's harder to cut the human out of a car just because it's hard to envision the autonomy. It's hard to envision autonomy being that capable, right?
It seems that they do the sharing control only in the sense of safety.
Yeah, they do more switch-based, right?
Right, whereas here you think about performance.
Yeah, we're
things
thinking.
to learn from this. They may be learning.
Yeah, I mean, I think actually a good parallel to a lot of the autonomy that we have in our system is actually things that we already see in regular cars, right? Like things like lane assist and parking assist and things like that. That's kind of where we're starting out at, which I think is a reasonable place to start for two reasons. One is that it still would be very helpful and it's kind of a viable technology right now. It also probably is more likely to be user adopted, so especially because people have now seen it in cars and are comfortable with the idea of something like giving them warnings because they're too close or something like that. And so that kind of like gradual introduction into the market makes a lot of sense to me. Yes.
How do you think the trust of the human, of the operator, the robot will impact the control? Because, for example, if there's a process meant they'll try to fight it more.
Yeah. So I see it, my guess is it will be sort of a continuous extension of the autonomy, the sharing control in the first place. So there's already we know that sometimes the human and the autonomy are going to fight each other. We hope not, but like they might, and it might, depending on what the human's doing, that might be the right thing to have happen, right? If the human's trying to drive into an obstacle, then we want them to fight because we want our autonomy to be stopping that from happening, right? And so I see the trust metric just sort of amplifying that, where if we really trust the human, we give them maybe a little bit more leeway, and if we really don't, then we tighten things in a little bit. But I don't think it'll be drastically different. I think it'll be a continuum.
How do you see the machine learning adaptive project that you're working on change with the different types of controllers?
Yeah, That's a good question. So actually the first entire year of this grant is that we are just gathering a ton of teleoperation data. So we're going to be having like 35 people without injuries, 35 people with injuries with different sorts, or like I shouldn't say with motor impairments from different sources, coming in and teleoperating both of the platforms in our lab and using probably 4 different interfaces. So both type of discrete limited interfaces and then a joystick probably in 2-axis and 3-axis mode. I guess for the wheelchair there's no point to 3-axis mode, so maybe only 3 for the wheelchair. And we're going to be gathering a ton of data, and so our first step is that we are just going to statistically look at how this data differs between different subject populations, differs with different interfaces, differs with different platforms. And then we'll see what it makes sense for machine learning algorithms to be expecting based on that, and we will design algorithms that are intentionally tailored to the data that they're expecting.
I really like the idea of using the confidence in the human for your fusion policy in the shared autonomy framework. My question is, in your computation of the confidence metric, do you take into account only prior kind of control commands and their effect, or do you also consider the current commands? Because it seems to me like people we can trust a lot, sometimes when they say they want to do something, it can seem completely irrational.
Yeah.
And so,
yeah, so in the work that we've done with the trust system, it was kind of and I probably should have explained this better, the autonomy and the human were not operating in the same space. So because it was this very dynamic system, the human was providing a reference trajectory, but the reference trajectory would perhaps be hard to stabilize to if they didn't have a good understanding of the system. And the autonomy is trying to track that. Now, but you're right in that we are going to be using trust in this way. In the Navy project that I mentioned that was getting started, we are going to be using it in this way to, well, I guess we're going to be using it to decide whether or not we need to shift discrete autonomy levels, so not at the level of like blending control like I was talking of, but it's true. That's certainly a consideration, is safety. Trust is a consideration, and whether or not those two should be like a part of the same metric or not, I think is something we would have to look into. There's also a question of when you're actually computing the trust metric, how quickly you should be computing it. So if the trust metric is changing all the time, it means that the autonomy, the behavior of the autonomy from the human's perspective is changing all the time, and it's kind of like they need to now adapt to a moving target, and actually might impede their performance because they can't predict how the system's going to behave, and that's a whole different set of questions.
We also plan to use brain-computer interfaces.
Can you speak up? Can you speak up?
We also plan to use brain-computer interfaces.
Not necessarily, only because, I should say, with the exception of the project with Sandro, the majority of the work in my lab actually is sort of interface agnostic in the sense that we expect we're getting control signals from somewhere. We're not. Our prioritization is that we're using commercially available control interfaces because that's what's broadly used out in the real world, and we want to build systems that are going to interface with that because it's just one less thing that needs to be adopted, or like a new thing that needs to be adopted by general society in order to get this technology out of the lab. So in our sense, we sort of categorize these by the dimensionality of the control signal and whether or not it's discrete or continuous, but where that's coming from could be anywhere. Brain-computer interfaces, so whether or not it's actually a viable technology in general, I think that implanted, like cortical brain and computer interfaces have really a lot of promise, but of course it involves a surgery. And so how immediate that technology is, it seems like it's still on the horizon in terms of if we think about like everyday people using it. If like skull caps, it's hard to see those ever being adopted outside in general society, and that's in part because of their appearance, that people aren't going to really be wanting to wear a cap all over the place. You just look more impaired, and also because the signals that you get are so confounded or conflated by the electrical signal of your scalp muscles that what you can do with it is sort of limited. So you can drive a powered wheelchair because that's a lower dimensional control space, but it's really hard to do like any kind of dexterous maneuvering with a robotic arm, with like the external surface EMG or EEG.
Let's get to one more question now.
So I think one of the motivations for shared autonomy is increasing the amount of trust that a human has in a robot. And one could argue that that could also be done if a robot had a really good predictive model of what the human wanted to do and was able to do that themselves.
Yeah.
Do you have any insights on how you could go about that, building such a predictive model that would...
Yeah. Not really. Mainly because it just seems like such a hard problem that we haven't even tried to do it. Because I think it's a really hard problem, and I think if you get it wrong, it's arguable how much you're gaining from it. And so we haven't even really tried to address it. So not that it couldn't be addressed.
So you were talking about how, like, with the human, in certain experiments, the human is the teacher and the robot, so it's training labels. So can you give an example of how, like, a non-impaired human might give training labels to a robot, let's say with a remote control versus an impaired human, and how that experiment would change, like how the training process would change? Just like a specific example, because I'm having trouble, like.
Well, so basically, all these systems are meant to be teleoperated by humans, and so you can get a bunch of demonstrations from that, nominally, whatever interface you would use just to teleoperate. Now, how good those demonstrations are is a question, and that's part of what I was saying needed to be addressed in this work, is like, what do demonstrations look like when you're using these limited control interfaces? And that just, it becomes even harder with people with motor impairments. So the experiment that I talked about is just teleoperation data. And so it's all just 100% human teleoperation, which is how these systems are just designed commercially. And so people are just trying to perform certain tasks with teleoperation. We can't do anything like kinesthetic teaching because that's not really reasonable. Maybe an aide could do it for the human, but certainly a human couldn't do it themselves. And not all robots are back drivable, so we don't really want to assume that. So I don't know, does that answer your question?
I guess I'm just trying to, like, understand a specific example of, like, what you would be training a robot to do, and then how the impaired patient would then be training that robot.
I mean, so what you would be training the robot to do is just anything you would want the robotic arm to help you with. So any sort of activities of daily living, you could imagine that it's like, you know, picking up something and pouring it, or being able to feed yourself, or doing different sort of toiletry routines, just sort of anything that the robot would want, you would want an assistive robotic arm to be helping you out with. So very, very sort of mundane around the house tasks.
So I have a question, actually. So this is my ignorance. So rehabilitation, is it a problem of trying to make someone who can do something and doesn't do it yet, or is it about finding out how much the person is going to be able to do? I mean, I'm wondering if there is like the concept that the person will be able to recover the whole thing.
Yeah.
Are there things that inevitably the person will not be able to do?
So usually, oftentimes, there are things that the human will never be able to do.
And so for those, why not have the full autonomy? I mean, I'll never be able to do something, right?
Well, it doesn't mean that they don't want to have input into how it's getting done, though. And like, you know, like if I can't operate my own arm, but I can use an interface like through my head to operate an arm, so yeah.
But on the other hand, rehabilitation includes also trying to have some
to regain motor function.
Regain the function, right?
So I'd say therapeutic rehabilitation is all about regaining motor function, but of course, I'd say rehabilitation more broadly is about regaining ability. And so like we consider wheelchairs to be a part of rehabilitation, even though it's not helping you regain any motor function, but you are regaining mobility. And so anything that sort of enhances human ability, we sort of, especially at RIC, we put under the umbrella of rehabilitation.
And so what is the difference between rehabilitation and assistive robotics?
So I say both of those because my lab kind of straddles the two worlds. So since we're always looking at robots that are meant to be teleoperated by humans, but it's just a struggle to teleoperate them, it's not necessarily like an autonomous, separate assistant robot. And so, but we're also not working in the space of rehabilitation robotics that doesn't have any autonomy. So we're kind of at the intersection of these two worlds.
Okay.
Yeah.
Final question, okay.
So in the shoulder demo, it looked like there was some kind of latency, or either maybe like it was really, really slow.
Yeah.
And so like, does that also affect the trust model? Because if the feedback cycle was really long, then I feel like I'm gonna not want to use this, or like I'm not gonna.
Yes, so that was, so you're right. That's, we're not doing any of the trust work with that system specifically, but also that wasn't the body machine interface system. I think that was the controller we had on the Miko at that time, which is now much faster. So I think actually it wouldn't come up anymore.
So one final thing is that when I visited, I did use one of the chairs. You should have brought the video.
It's true. I wonder, I think I maybe have it. No?
So I used the one that was
the head array, right? Yeah.
Go through this door.
Yep.
And it was quite an interesting experience to see that actually that thing reacts to what you are doing. So I got used to, I did a few times to just press the here, and the thing would go forward, move
Yeah.
like this, forward to the left. But I hit the door a few times, right? So,
Yeah.
but on the other hand, it is something that that enables, the thing to move as you apply those actuators with different things than your legs.
Yeah.
So so I have this video of me on the wheelchair.
You sure you don't want? I think I have it. I think so. Everyone wants it, Manuela.
So they can see how hard it was. I'm not impaired, but still.
I don't think I think I started. I think I started. I think I think I started it too late. That
Exactly.
You weren't.
So and I see. I'm like trying to look at this. I'm trying to move.
You don't know where it's going.
And I cannot move anything, and the Brenna is giving me instructions.
No, it's not. Yeah, so you're using the joystick now. That's a header right.
Yeah, joystick, and then I kept telling her.
Oh, I think I shouldn't be showing this. I think this is, right, no. It was in full teleoperation mode, not autonomy. But yeah.
So anyway, you can stop this.
Yeah.
It was quite an experience.
Yeah.
In fact, very kind of like interesting to understand how difficult this problem actually is to create an autonomous device that you are familiar with, like a wheelchair, to really do the control for you. I mean, we did do like the autonomous part.
We did, yeah. I think it was before that. I started filming too late, so.
Okay, I think you have it.
Just the concept of human in the loop only means that the user can give commands to the robotic hand. I mean, with the body-machine interface or the vast variety of use, as you said. I mean, the robotic hand is already equipped with tactile sensors. I mean, why not make the human as a component in the loop actually feels how the robotic hand is grasping or touching the object? What's your
I'm sorry,
stand?
I don't think I understand your question.
What do you think about how human can actually feel their existing device instead of only giving commands to it?
Yeah, so that's so if I understand your question correctly, that is actually something that I didn't touch upon in this talk, but is also a big question, is actually how you partition control. So not just control sharing. I just talked about it in terms of human and robot, or largely I talked about it in terms of human and autonomy are issuing control signals in the same space. And so what you're figuring out is how to like blend or arbitrate. But an example I had actually with the body machine interface, right, was that it was mapping to actually an alternative control space. It was mapping to this sort of piecewise transition between piecewise functions and also to speed. And so this question of like what the human commands should actually be mapped to and what is going to be most intuitive for these systems also is an open question.
But I do think that it was very compelling, the fact that I was driving the robot through the person. He hit the obstacle.
No.
The usual thing that we sometimes do. But it was very good because the autonomy takes over your safety. So if you were not okay, well, one final question.
Maybe I missed it, but is there other kinds of feedback from the robotics other than just visual? Like just looking at it, making sure it's stuff. Do you actually get feeling back maybe like in the interface to feel that like the arm is in a particular position or it's holding a particular weight or feel some certain amount?
So it's never prosthetic limbs. It's always, okay. So it's, no, so there is not feedback like that. And the question of how like bidirectional the information should be is like, I'd say a separate and very important research area. So far, we focused on if we had no autonomy, what's the sort of interface you had? And then how can we sort of seamlessly insert some autonomy that is just still working with that basic interface? Now, of course, if we gave some feedback back to the person, especially I think with the arm, knowing like what control mode it's in, things like that, is all very important information to give to the human. And so that like we're not interface design experts, but that certainly is a worthwhile thing to have on these systems. So maybe that would be a collaboration. Maybe it's something we'll look into ourselves. I'm not sure.
Okay, let's thank Brandon one more time.